Yeah, so my name is Greg Hellbourg. I'm Institute of Technology in California, and I'm also the spectrum manager of the Owens Valley Radio Observatory, which is a radio observatory owned by Caltech, which I'm going to present in a couple of slides. But I wanted to start off this talk showing you this image, which is an image of the center of our galaxy. This image has been produced by a radio telescope called Meerkat. It's a telescope that is in South Africa, in one of the most quiet, radio quiet areas of the world. And the reason why I'm showing you this image is not because it's beautiful. I mean, it is beautiful, and it's great to see, and to see what radio astronomy is about. But it's also to motivate the reason why we're doing radio astronomy. There's no way we would be able to produce such an image with optical astronomy, because there's just too much dust, stellar dust, in the middle of our galaxy. So pointing optical telescopes towards the center of our galaxy would not show anything. And this is what radio astronomy is all about. Now, going back on Earth, what do we do with radio astronomy? So we have those big dishes that you probably all have seen in movies and documentaries, and you've seen images of. And we turn those telescopes towards the sky, and what do we get? Well, we don't get much. Because although the emission processes, the astronomical emission processes are very energetic, right? It's high energy processes that are in place. Well, those emitters, if you will, they are really far away from us. So we get a lot of attenuation from those signals through large distance propagation, but also because the universe is not completely empty. It has lots of interstellar medium, intergalactic medium, even between galaxies. And even our own ionosphere has a tendency to absorb and filter out some signals. So we don't really look at astronomy the same way as communication people look at RF signals. In fact, we don't really even use the watt as a unit of power. We talk about astronomy energy as spectral power flux density. And we have our own unit to describe the power of a source, which is the Jansky. And the Jansky is 10 to the minus 26 watts per square meter per hertz. It's named after Carl Jansky that we see on the right of this slide, which was the kind of the first discoverer of astronomical radio emissions. And I like always to put everything in perspective with this Jansky, the unit, to tell you how weak of a unit this is. So I like to think of what if we're using a cell tower to look at a 1 Jansky source. Okay, 1 Jansky source is a pretty bright source in a radio astronomy, all things considered. So if we were to use a cell tower, so if we're observing, for instance, this 1 Jansky source with a 5 megahertz bandwidth and at a 880 megahertz frequency, then the signal that we would effectively see, assuming that the antenna is isotropic, would be of the order of minus 183 dBm. That's how much power that 1 Jansky source would produce at the output of our antenna. The typical cell tower sensitivity, how a cell tower is capable of detecting detecting a user equipment, a cell phone, is roughly minus 90 dBm. So we're like 90 dB below that threshold of sensitivity. Very, very weak signals. And this is for a 1 Jansky source, and current telescopes, they observe micro Jansky to nano Jansky sources. So we're a few orders of magnitude even weaker than that. Now, how do we do for building instruments that are sufficiently sensitive to these kind of sources? Well, we do have 4 main characteristics, 4 parameters that we use to tune new generation radio telescopes depending on what kind of science we want to do with those telescopes. The 4 parameters are the noise temperature of our receivers, and to reduce that, to optimize that noise temperature, it's often water or cryo-cooled receivers that go down to a few kelvins of system noise in our receivers. Another way we increase the sensitivity is by using large collecting areas. Right? We have like very large single dish telescopes, such as maybe you're aware of Arecibo, that doesn't exist anymore, but used to be a 300-meter dish radio telescope, so that's a massive dish antenna with very large collecting areas. China built the 500-meter dish telescope called FAST. But there's also a new trend of building arrays of telescopes, which helps us producing cheaper to maintain and easier to maintain in general dish telescopes, but a lot of them so that the collecting area is still very much preserved. Then we have integration time. And you can think of radio astronomy observations like the exposure when you do photography, right? The more you expose, the lower the noise becomes. And we can do exactly the same in radio astronomy. But instead of having exposure times of, I don't know, like a few milliseconds, we use seconds to hours to sometimes weeks of observation. But it's okay because what we're observing, it's usually stationary signals, stationary in time, which means that whether you observe it today or last week or next week, things will not really change. So we can actually effectively observe things for weeks, even split into different time chunks. And finally, another very important parameter that we exploit is the bandwidth of our receivers. The great thing about radio astronomy is radio sources, they're wideband in nature, right? Nature doesn't produce narrowband signals. So whether we observe it over 5 megahertz, 10 megahertz at like very low frequency or very high frequency, the astronomical signal that we're trying to find, that we're trying to observe, will emit at all those frequencies. Depending on what kind of source it is, some region of the spectrum might be more appropriate for detecting some signals, some of those sources. But basically, there's never too big of a wideband of a bandwidth for our receivers. That's why nowadays we're working with a few hundreds of megahertz of instantaneous bandwidth receivers to even a couple gigahertz for the widest receivers that exist. The problem, of course, is that as radio astronomy users, we have to share the spectrum with active users, right? We're completely passive, we don't transmit anything, but we have to deal with people who transmit things at other frequencies. And radio astronomy has some frequencies that are allocated to the radio astronomy service, which you can find in the ITU documentation. I'm sure the ham license will touch on that as well. But basically, less than 3% of the spectrum under 30 gigahertz is allocated to radio astronomy. It's not much. So it is common practice for us to observe outside of those bands and have to deal with what we call radio frequency interference. It's not interference from an FCC point of view, from the regulator's point of view, because those signals are allowed to transmit. But it is interference for us because it's just not a signal that we want to observe, right? So we're very used to passive spectrum sharing. So I mentioned the Owens Valley Radio Observatory, which is the radio observatory that I work for. I'm on campus at Caltech, so near Los Angeles. But our radio observatory is far away from any big metropolitan areas. It is located, it's this red star on the map of California. So very close to the border with Nevada. And we're in a valley, and valleys are great for radio astronomy. The reason for that is that the mountains, the surrounding mountains, offer a proper, natural RF protection. So, even though we are far away from metropolitan areas, we have also this protection from the mountains, surrounding mountains. It's not exactly a radio quiet zone. We have a couple towns, Bishop and Big Pine, California, that surround the observatory. But it's not that much of a concern currently. Our observatory runs many different experiments and instruments. We have some instruments that are science ready, but our university is also a technological university, and we do a lot of research and development for new instrumentation. So this gives you a little idea of, a good idea of what experiments run at OVRO. In the lower spot of the spectrum, between 0 and 100 megahertz, we have the long wavelength array, the LWA. Then on top of that, around in L-band, so above 1 gigahertz, we have the Deep Synoptic Array 110, which we're going to talk about longer later. We have a solar array, the Expanded Owens Valley Solar Array, EOVSA, 1 to 18 gigahertz, 500 megahertz of instantaneous bandwidth. We have a large 40-meter dish, and we have a CO mapping array. And we used to have the Karma array, which doesn't exist anymore. It's been decommissioned and removed, but our observatory used to go up to 265 gigahertz in frequencies. So as I mentioned, we work a lot in research and development at Caltech. And there is a shift that we're kind of trying to investigate. We've been trying to investigate since 2013, which is, back in the days, we used to build telescopes, like perfect telescope, very clean, very pre-calibrated, and have a simple digital receiver, even analog receiver in even older times, but simple digital receivers that would produce like spectra that are great. Like no need for calibration. Everything is taken care of because the quality of the antenna is so great, but very expensive. But as we've heard previously, Moore's law just keeps increasing. The number of transistors, the amount of computational power available, and the cost of the computational power. So our concept is, what if instead of building those very expensive telescopes, we just use off-the-shelf antennas, dish antennas, like satellite dishes, and a lot of them, and all the signals plug into massive GPU servers. And we take care of the calibration and the corrections of the data just using algorithm, right? And this is what we've been working on. So in 2013, we had our first dish that was just built as a prototype to measure noise properties of the receivers and see what are the limitations, how many antennas would we need to reach a right sensitivity to produce science. 5 years later, in 2017, we had the DSA-10, which is 10 antennas, just incoherently summing the data of all these antennas. These were like literally ordered on Alibaba.com. I think they just arrived in California. We set them out, and they wouldn't move. There's no motor, nothing. They just point at the sky, incoherently sum together. We get great spectra. We detect what's called fast radio bursts, which are transient astronomical signals. That's great. A couple of years later, 2019, we completed the DSA-110. So this time it's 110 antennas, 4.65 meters in diameter. And we're still tracking those fast radio bursts, but it's not just a matter, at this time, it was not just a matter of detecting those fast radio bursts, it was also a matter of localizing it. And if you don't know what fast radio bursts are, I'm sorry, but I will not talk about that, but it's a very important subject in astronomy. It's basically, like we don't really understand those effects. It's just very bright pulses that are detectable. We just don't know where they come from. So detecting is one thing. Localizing them is something that's even more important. And then DSA-2000, which we're going to talk a little bit longer later. DSA-110, well, as I said, it's 110 antennas. That's what it looks like. Actually, that's what exactly it looks like. There's like a massive T of 95 antennas. That's the yellow T at the center of our observatory. And then we have a lot of outriggers. And basically what we do is we beamform the data from from the 95 core antennas to get high sensitivity capability towards the sky to detect fast radio bursts. Whenever a fast radio burst is detected, then we download roughly a couple seconds of data from all the 110 antennas. We correlate them and we image the field. And from this imaging process comes localization, because we're going to detect where that blip of color, of energy comes from, basically. So that was our main driver. But then it's achieved, it works, it's operational, and now our next challenge is the Deep Synoptic Array 2000, DSA-2000. So this time, it's no longer 110 antennas, it's 2,000 antennas. And the motivation, the scientific motivation for this telescope is to be a survey instrument. So there's another paradigm shift happening in radio astronomy, which is instead of building telescopes that are what's called PI-driven, which means as an observer, as an astronomer, I can apply for time on telescope, and I say, okay, I want to do this kind of science. I'm going to be the sole user of that telescope from this time to this time, and I do whatever I want, and I own the data, and I publish them, and that's it. Now what we want to do is produce survey data, which means we survey the sky. We produce data that are useful for any kind of science, or as most science as possible. In fact, we want to maximize the amount of science achievable per bit of data, if you will. So survey instruments, they have two characteristics that are, that kind of characterize the survey instruments, which are the sensitivity and the survey speed. So the sensitivity is how weak of a source can I detect with my telescope, and the survey speed is how much time do I need to detect that source. And so this diagram shows a comparison of a few edge instruments that exist right now, and it shows the survey speed versus the sensitivity of survey instruments. And we want to be on the top right of this diagram, right? We want to be sensitive and we want to be fast at detecting sources. To do so, we're building 2,000 antennas, dish antennas. They're all 5 meters in diameter. They're in a pretty dense core formation footprint. We're covering 700 megahertz to 2 gigahertz, which is another reason why we're so sensitive. It's because we're in the most sensitive region of the spectrum from a radio astronomy standpoint. We're going to achieve 3.3 arc-second resolution, so the footprint of the array is 19 kilometers by 15 kilometers. It's huge. We've been surveying a lot of valleys in the US to put this telescope. So the telescope is not built yet. We're planning on starting building it in 2016, but this is where we're at now. So the reason why we have 2,000 antennas, it's very interesting. There's no way for us to store the data of 2,000 antennas, because what an interferometer does is it correlates the data between all the antennas together, right? So when you have 2,000 antennas, that means that effectively you have a 2,000, in fact 4,000 by 4,000 matrix per frequency channel. You might have like hundreds of thousands of frequency channels, and these correlated data, you can either produce them every second and store them and have someone years from now trying to image this, or we can try to image in real time. And this is what we're trying to do. We're trying to build a radio camera, so a camera that effectively in real time produces an image of the sky that is of scientific relevance. So 2,000, the one advantage of having 2,000 antennas is what we see on top is the very large array, 27 antennas in a Y formation. And you can imagine the VLA, the very large array, as being like a CCD matrix of a camera that has only 27 pixels and in a Y shape. Well, there's going to be an artifact which we call the point spread function. It's like the telescope response to the data, which we see. That's the second plot right to the right of the image of the very large array. And basically, when we image the sky with this telescope, what we're going to get at the output is the image of the sky convolved with the point spread function of our telescope. And it's very dirty, as you can see. That's the top right image. And to actually do science with this kind of image, what we need to do is run a heavily complex and heavily nonlinear as well algorithm that does a deconvolution. So we roughly estimate the point spread function of our telescope, and we deconvolve that point spread function from our image. When we have 2,000 antennas, this is the bottom row, our point spread function is pretty much a Dirac. It's a 1 pixel. And we produce images of scientific relevance right away without having to deconvolve anything. So not only we want to be fast and sensitive, but we also want to do it cheap. So cheap as in the cost of a single antenna should not exceed $25,000. And this includes receiver, all the equipment, and also the RF over fiber, drivers, and everything. So we do have a structure which is roughly, sorry, not roughly, but it's commercial mostly commercial equipment. Our feed is, we call it the cake pan feed because it's actually made of an actual cake pan. It turns out cake pans are, have really good RF properties with very low loss. So we're designing that at a very low cost as well, and we have a cryogen-free wideband LNA that reaches an incredible noise temperature of dozens of Kelvin, which is very very incredible. But that's not it. The main the central core of this radio camera is this: how does a radio camera works? So we have a front end. The front end is, again, completely commercial, right, off the shelf. The front end is I-Wave RF system on module that includes ADCs. From those ADCs, which sample the data coming out of the dishes, we channelize the data, right? So we split the data into sub-frequency channel. So we have at the input roughly 2 gigahertz worth of bandwidth, and then we go down to 130 kilohertz of frequency resolution. And then we apply a massive data transpose, where at the beginning of our system, we have, for one antenna, all the frequencies. What we want after this massive data transpose is that one server will see the data from all the antennas, but just over a small chunk of frequencies, right? And those GPU servers, what they're going to do is they're going to first correlate the data together, then flag and calibrate those cross correlations. That means basically detecting cross correlations that don't really seem right. It seems like there's an issue, maybe an artifact in it, so we just remove them. Everything runs in real time, so we need to remove them because after that there's no way to get back to the data. We grid, which is it's also an algorithmic step of the imaging process, and then we image using a simple Fourier transform. And what we get at the output of that is narrowband images, images produced over 130 kilohertz channel, but we can completely sum them together to produce an actual image that scientific can use. So yeah, this all runs in real time. And we're currently demonstrating this real-time imaging with the long wavelength array, which I mentioned. It's one of our low-frequency instruments, 0 to 100 megahertz. And what you see to the right, it's slow, but it moves. It's actually an image, a video of the real-time imaging process, right? So what you see is basically the edges of the circle is the horizon. The center of the image is the local zenith. And we see the Milky Way that comes across. Occasionally we see satellites and airplanes that are those bright spots that come through. So yeah, so that helps us prototype and validate the concept of the radio camera. Now, I also mentioned that earlier. RFI, so radio frequency interference, is a major concern in radio astronomy, and especially for DSA-2000, because we're covering 700 megahertz to 2 gigahertz, which is mostly L-band, and it's also one of the most heavily used region of the spectrum. We can dissociate from this frequency range the 300 megahertz at the bottom and the 300 megahertz at the top of the band, which are mostly site dependent. It contains allocation for cellular services, so mostly cell towers, but also point-to-point microwave and public safety systems. And that's true at the bottom and at the top of the band. And the middle of the band is mostly used for aeronautical, so ADS-B and DME signals from airplanes. We have GNSS, GPS, Galileo, and so on. Satellites, we have lots of satellite communication, geostationary satellites, downlinks, and the Department of Defense that's using this range as well. So to find a site for the DSA-2000, one of the first data that we worked on and analyzed is the distribution of cell tower across the US, and this is what you see here. So each tiny dot, your eyes will definitely not be able to resolve individual dots, but each individual black dot represents one cell tower, and it's pretty easy to see that the US is kind of split in three regions, right? There's like a half east with like high population density, so high cell tower density. The West Coast, which is also high population density and therefore high cell tower density. And then there's the big middle where there's not much population, so not much cell towers. And Nevada in particular is a very interesting region for us because not only it has low population density and low cell tower density, but it also has valleys. And we're very familiar with building observatories inside valleys, and we love this protection that the mountains show us, give us, RF attenuations. So we went out to many regions. There's a whole process for site selection that we ran, but I just wanted to talk about the actual survey, on-site survey. We use, it's funny because I didn't know Aeronia was here, but we worked a lot with Aeronia for this survey. So we used this Spectrum V6 spectrum analyzer, which has roughly 200 megahertz, I think a little below 200 megahertz of instantaneous bandwidth. And we plugged this on a passive active omnidirectional antenna. And we basically ran, we drove through the valleys to capture what the spectrum looks like in different spots of the valley. This shows you an example of one of our main candidate site candidate. By the way, we haven't officially announced our site yet, but this is one of our main candidate sites. In blue, you see the footprint of the telescope, where the telescope would be if we were to select this site. In red, the spectrum monitoring regions, and in green, the cell towers nearby this valley. And then you see the various spectra captured at all these different points. And the thing that's the most impressive here to see is you see the number one, the spectrum at the bottom right. It's not on the telescope footprint, but it is kind of in line of sight with that bottom cell tower that you see at the southernmost cell tower. And you see the activity at the bottom and the top of the band in the spectrum in blue, right? You see those large signals, which are just the downlinks of that cell tower, which you don't see anymore in all those other spots, the 7 other monitoring points or sites. That's just because the mountain naturally provides us with roughly 40 dB of attenuation from that cell tower, which is great. We're not only basing all our decisions on site selection on RF monitoring, but we're also using external data such as weather data. We have aeronautical data, which it's this histogram that you see on top of the slide, and we also use studies of satellites, how satellites are going to impact us, which they're a big issue. In fact, talking about satellites. One of the main threats, I don't know if you're aware of that, but earlier this year, the FCC approved the use of the direct satellite-to-cell services, right? Which means that frequencies that are currently allocated to cell towers are now potentially being used by satellites to provide you with cellular service directly from the satellite to your user equipment. Great news if you're in the desert or if you're in like a very remote place where, I don't know, AT&T doesn't want to put up a cell tower. But the problem is that all the bands that are allocated there to this service in particular, they all fall in our band. So we're working actively on trying to find mitigation solutions to these. In fact, one of our main mitigation solutions that we're working on right now is a tunable quad-stub resonator filter. So it's a notch filter that can be turned on and turned off with a varying center frequency to notch out whatever data gets in our signal chain, just to avoid saturation. We also have a full RFI mitigation and flagging pipeline that we're implementing, but I won't get into that. This is my summary slide because my time is up. But yes, the summary is we're working on DSA-2000. There's a website there, and also my email address if you're interested in talking more about this. We're covering 700 megahertz to 2 gigahertz. We're going to be in Nevada, site to be announced hopefully soon, hopefully early next year. And yeah, one of our main concern is interference and active transmissions, which is where I spent, I don't know, like 600% of my time on for the past couple of years. Yeah, and construction planned in early 2026, so stay tuned. And I'm happy to take questions if we have some time, but probably not.